Hi, everyone. We are going to do this problem from the Nearpod activity. Determine the force of gravitational attraction between a 78 kilogram boy sitting 2 meters away from a 65 kilogram girl. Circle your answer and include units. So we're going to go ahead and do this one together. I'll open up my whiteboard, and the first thing we're going to start off with, as always, is a picture. So here is my 78 kilogram boy. He's sitting, let's make them, they're going to be on a picnic. Okay, so he's 78 kilograms, and they're on a picnic. So here they are. I guess they need like a blanket. Here's their blanket. And here's the grass. It's very nice. He should probably have some arms. And then she's going to be 2 meters away at the other end of the blanket. And she weighs 65 kilograms. And they, because of the law of universal gravitation, are attracted to each other. We need to specify that they are 2 meters apart. So they are attracted to each other, but it is just a really, really, really small force. So that's why when you're sitting 2 meters apart from someone, it's not like you can feel their gravity sucking you in. Maybe metaphorically you can feel that, but physically you shouldn't be able to feel it. And that's just because it's really, it's going to be a really, really, really small force, but it is a force and it exists. So let's go ahead and calculate it. To get the force of attraction, we're going to use that universal gravitation formula. So that's going to be big G times mass 1 times mass 2 over r squared. So let's just sort of fill in what variable belongs to what variable. So our guy here, he can be M1. I'm going to go ahead and sort of move them down a little bit so we can draw some arrows. So he can be M1. We will make her M2. This 2 meters, that's going to be our R. And then G is a constant number. It's always the same no matter what the circumstances are. G is always the same number, and it is called the universal gravitation constant. And if you can't remember the number, you don't need to memorize it. You can always just Google it, which is what I do because I can never remember things like that. So we will just type in universal. See, I already searched for it earlier today, so I like automatically came up on my on my Google. Universal gravitation constant, and it is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. So let's go ahead and write that down. So 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. Should be a times in there. Yeah. And that is a really, 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 really small number. And you can tell because it is written in scientific notation. And usually we only write things in scientific notation if they are either very, 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 very big or very, 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 very small. And we can tell the difference because of the sign of the number that the 10 is raised to. If it is a negative sign, that means we're going to the left. If there was no sign or it was a positive sign, we'd be moving to the right. And since this is negative, we're moving to the left. So if we were to write this out not in scientific notation, it would be 6.67. And then we would have to move this decimal point over to the left 11 times. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that would be the new place where the decimal goes. So it would be a 0 every single spot that we created here. So the actual number is 0.0000000000667. And that is so small. Obviously, it's easier to just write it in scientific notation, which is why we do that. But I just wanted to give you guys a little refresher on what scientific notation means. So since the 10 is raised to the negative 11, we move the decimal to the left 11 places. If it had been raised to 11 and it was positive, we would have moved it to the right, and then we would be talking about a really, really big number. But we're not. We're talking about this super small number right here. So if scientific notation really like freaks you out, especially putting it in a calculator, which honestly, to this day, sometimes I just get like, whoa, there's too much going on. There's like exponents, there's multiplication, there's decimals, like it's just a lot. I will sometimes put it out like this, and I will put it into the calculator like that, just because I feel like there's like less chance of me making a mistake when I'm typing in the calculator. So you can totally do that. But I will also show you some tricks for calculating with them when we get to the point of this problem where we are doing calculations. So, which we're almost there. We've got all our variables figured out. So let's go ahead and sort of move ourselves up here. And we're going to plug our variables into the equation and see what we get. So we know what our big G is. It's 6.67 times 10 to the negative 11. I'm going to run out of room. We are going to move that. We're going to put it down here so we don't run out of room. Okay, sorry. Oops. And that's newtons times meters squared over kilograms squared. And then we are multiplying that by, so multiplied by this fraction that we are going to be setting up, which is going to be our M1, was the weight of our boy, and that is going to be multiplied by our M2, which is the weight of our girl, and that is going to be over R squared, and our R was our distance between them. So the radius, and that's 2 meters, and that is going to be squared. So we've got all of our variables plugged in, and now we just need to figure out like where to start with order of operations and everything. And the place you should always start is with the exponents. So down here at the bottom, that's where we're going to start. 2 squared is 4. So since this is kind of separate from this, we're going to like deal with this fraction first, and then we'll get to, once we've got that all just into a whole number, then we'll worry about multiplying it by the scientific notation and the constant. So let's deal with this fraction first. So I'm going to go ahead and change this to 4 meters squared, right? Because 2 squared is 4. And then the square also applies to the units. So if we've got meters in here, meters, now it's meters squared. And then up here, 78 times 65. I'm going to go ahead and just throw that in my phone calculator. Don't feel like I need to walk you guys through how to do 78 times 65 in the calculator. You end up with 5,070, and then it's going to be kilograms squared because you had kilograms times kilograms. And we can further reduce that down if we want to, and by doing 5,070 divided by 4, we get 1267.5, and our units are going to be kilograms squared over meters squared. So now we've got a whole number on like that side of the math situation. And so we can worry now about how to multiply it by our constant over here, which again is 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. There's times there. So let's go ahead and go to Google. We're just going to use Google, like the search bar, as our calculator, and we're going to calculate this out. I'm going to move everything up for us so we have some space, and we're going to go to Google to figure this out. Yeah, I want to go. What is happening? There we go. Here we go. So we're going to use this search bar, and we are going to use parentheses to put our scientific notation inside. And we're going to say 6.67. Multiplication in like computer speak is the star. Times, but actually we don't need to do the times 10 to the negative 11 because we can actually use the school trick, which is E negative 11. E in computer speak stands for times 10 to the. So the times sign, the 10, and the raised sign, all you can just replace that by E, like a lowercase e, whenever you're working on a calculator like this. So just 6.67 e negative 11, that means 6.67 times 10 to the negative 11. And we are multiplying that by our 12, ooh, I forgot it. Let's go back really quick. 1267.5. And we'll close the parentheses, press enter, and we end up with 8.45. Remember, the E is times 10 to the. So it's 8.454225. We're going to round to the 100th place because that's just what we've been doing this whole time. So 8.45 times 10 to the negative 8 is going to be our answer. So let's write that out and make sure our units check out, and that'll be our last step. So force of attraction is 8.45 times 10 to the negative 8. And let's look at the units. We've got, I'm going to write them over here on the side, newtons, and we've got meters squared over kilograms squared, and we're multiplying that by kilograms squared over meters squared. So I just like took away the numbers and I'm just looking at the units, and it looks like the kilograms squared and the kilograms squared are going to cancel out. The meters squared and the meters squared are going to cancel out, and the only unit standing is newtons. So our units are newtons, and that makes sense because what we were trying to calculate was a force, and newton is the unit of force. So 8.8 or 8.45 times 10 to the negative 8, again, such a small number. Just to put that into context, that is going to be 845, and we're moving it from this spot 8 places to the left. So that means it's going to have 1, 2, 3, 4, 5, 6, 7, 8. New spot for the decimal. So 0.000000845 newtons. That is the force of attraction between this boy and this girl on this picnic. It's so small, and obviously they're not going to feel it. This is why you don't feel the force of attraction between you and other people or between you and anything. I mean, you could be sitting on a chair and technically there's gravity between you and that chair, but it's so small. You could be holding a ball, and again, there's going to be gravity between you and that ball, and it's going to be so, so, so small. But this is why the force of gravity, there goes the bell, on Earth is 9.81, because the Earth is massive, so big. So even though the universal gravitation constant is super, super small, it's multiplied by the mass of the Earth, which is humongous. And the radius of the Earth is also pretty big. But we are, compared to like the moon, for instance, we're pretty close to the center of the Earth. So the radius would get a lot bigger if we got further away from Earth's surface. If we were like flying to the moon. But the Earth is just so big that's why we end up feeling this gravity. And that's obviously going to be multiplied by our weight to make it into newtons. So our mass. But the 9.81 comes from this equation, but with Earth as the one of the masses, which is why it's huge. Okay, sorry, I'm going to stop rambling. Hopefully you guys are feeling good about these problems, because we're going to do a couple more practices next.